Hi everyone. This is the second part of the video for Chapter 8, and again you want to watch this before you try to complete your homework in number 18. In the previous video we were testing a claim about a proportion, and in this video we are going to test a claim about a mean. So this is very similar to what happened in Chapter 7, where we had two different types of confidence intervals, one involving mean and one involving a proportion. The same thing here now. We can test claims about a proportion, or we can test a claim about a mean. So let's go ahead and take a look at a question and see how we proceed. So I wrote up this question. It says, we have the response time of rats. So think of it like how quickly they react to something. And the response time of rats has a mean of 1.2. So, oops. And a drug company claims that their drug will improve that response time. So my guess is this drug is sort of like a caffeine type drug, right? And we often do tests on rats before we bring them on to people. So they're making this claim here. It's right here. The drug company claims our drug will improve that response time. So there is our claim, meaning they'll improve a time of 1.2 seconds. So in other words, that response time will actually go down. It'll be even faster, maybe 1 second or so on. So in order to justify this claim, they did a test of the drug, and on 100 rats, that was their sample size. 100 rats were injected with the drug, and the mean, and the reason I put this little line over this is because it means the sample mean response time was 1.05 seconds with a standard deviation of 0.5 seconds. So notice the difference in this question from a proportion question, where they usually tell you how many people had a success out of a total number. This is looking at a very specific mean time and with a standard deviation. So just a different type of question, different type of claim. We need to test the drug company's claim to a 0.05 significance. All right, so we are the statisticians asked to test this claim and to find out if the drug company can make this claim that their drug will improve response time. Okay, so how do we do that? Well, let's first look at the steps like we did with the proportion. Steps for testing a claim about a mean. You're going to notice it's very similar to testing the claim for a proportion. In fact, step number 1 right here is exactly the same. Determine the null hypothesis, the alternative hypothesis, and identify the claim. All right, so let's get ourselves a clean screen here. And we'll start with step number 1. I'll come back to the list. What is our null hypothesis and what is our alternative hypothesis? Well, just like before, our null hypothesis is actually always going to be an equality, and our alternative hypothesis will be some sort of inequality. But now instead of a proportion, we are talking about the mean. Okay, and I don't have the question in front of me, but the mean, we were told that it would improve a mean time of 1.2 seconds. That was the claim of the drug. So here is where the mean is going to equal exactly 1.2 seconds, okay? And therefore, this means the drug does not have an effect. But the claim is here in our alternative hypothesis, which is claiming that the response time will actually improve, meaning in this case it will be less than 1.2 seconds. Okay. So there is our claim right there. So very similar to the last type. Okay, what was step 2? Well, step 2 in proportions we had to find the sample mean. The sample proportion, but in this case we're just actually given it, so I'm just going to jot it down. And in the book they use an X with the line over it. I'm just going to use the mean because we're so comfortable with that symbol, but as you know, the hat over the symbol of mu means the sample mean. And so on our 100 rats, their response time on the drug was 1.05 seconds. And the sample standard deviation was equal to 0.5 seconds. All right, So we've just identified those parts. Okay, so step 3. Let's go back to our directions here. And, oops, not that one. Here we go. Step 3. Messing up mine. I didn't have a step 2. This should actually be step 3 here. Oops. Keep doing that. I'll learn this one of these days. Get down here. There we go. Step 2 should actually be identify the mean, the sample mean, and the standard deviation, and this now becomes step 3. But just like before, step 3, this will be 4 and this will be 5. Step 3 is to draw our normal curve. We need to find the critical value, and we need to shade the critical space. What's going to happen here, and I'm just going to talk about this briefly, we've always at this point found a z-score, and the formula for that z-score is still going to stay the same. However, now what we might occasionally have to do when we're looking at our critical value and critical space is sometimes we have to use a t-table and find the t-table rather than the z-score. And I'll show you how to do that, and I will always tell you which type of table you need to go to. It doesn't add any extra work to your problem. So let's go back here to our problem, and I'm going to go over to the side now and draw our normal distribution curve. Oops, doing that. Okay, here's our curve. I'm going to put this right here. And our curve is still the same as always with our mean is equal here, 1.2. And this is where our z-score is 0. So we still have a normal distribution curve. Okay, I'm going to put this down blue to find this. And we are told they wanted a 0.05 confidence, 0.05 confidence. And again, because this is less than, we have ourselves a left-tailed test, So that means this space right in here is 0.05. And again, I'll add those 2 extra zeros, and this is our critical value. Okay. All right, so I know you guys know how to use the z-table to find that z-score. And if you look it up at 0.0500, the area under the curve, it will yield you a z-score of negative 1.645. Okay. But sometimes on the homework, they want you to use the the t-table instead of the z-table. So I just want to show you that the difference is basically insignificant. I'm going to close this out. Let's bring this up. No, that's our t-tailed test. Let's go down here. Where was it? No. This one. Here we go. So in your packet of tables that I gave you, you're going to notice after the first page of positive z-scores and negative z-scores, the very next table is called a t-distribution critical t-values. It's just, these are critical values. So just like before, you were going to the t-table to find those, the z-table to find those critical values. We can do that here as well. It's just a simplified version. It's less accurate when you don't have the same amount of data. And we basically use it when the population standard deviation is not given. Okay, which in most cases for a testing of a mean, that is the case. So really all we do is there's 2 parts to finding this. We have something called the degrees of freedom, and then you can see you've got your 2 types of tests. You got your area in 1 tail and your area in 2 tails. So if you notice on this problem, we were area in 1 tail. We had a left tail test for this problem, left-tailed test. So we're in 1 tail, and we wanted a 0.05 significance. So that's right here. That's right here. That is this column here. Straight. This is the one we're going to be looking at. Okay, and then the question is, which of these numbers do we use? Well, then we go to n. N in this problem was 100. We injected 100 rats with the drug. So n is 100. Now, normally, you would subtract 1 and you look up the number 99. But in this case, because 100 is so high, we're just going to have to use that. This is what we call the degrees of freedom. Okay, or sometimes it's written as DF in your book. And if n is less than what it looks like about 40, then you will subtract 1 off. So if you had n equals 40, you would actually use 39, n minus 1. Degrees of freedom, we always use n minus 1. Okay, should write that n minus 1. N minus 1. Okay. But in this case, 100, we go from 90 to 100 to 200. So once you get over 100, you're going to always use the z-table. But here we go. We had a sample size of 100 over to our 0.05 column. And notice this number right here. I know it's tiny, but it says 1.660. 1.660. So let's go back to our, close this out and open this back up. And oops. I'll go here. One of these days. Nope, there's my question. Where are we? Nope. Here we go. All right, finally. Okay, so what you're going to notice, I'll just take a different color here. Let's do green. That our critical value, z is equal to minus 1.645. Well, t was equal to minus, and because it's on the left side, we know it's negative 1.660. So look, these differences are absolutely minuscule. They're minuscule for finding the critical value. But that's just a quick help with how you use the t-table if you need to. All right, and on any work that I would assign you in class or the project or anything, I will tell you whether to use a t-table or a z-table. But in most cases, I always say just use the z-table. Okay, so now we have defined our critical value and our critical space. All right, so C-table, C-graph. All right, so step 4, just like in our previous types of problems with proportions, the next step is to find that, oops, wrong color there, find the test statistic. Find the test statistic. So let's do that. And the test statistic is just a z-score that we are going to, or in some cases a t-score, but the process for finding it is exactly the same formula. We are going to take, just like we've always done with the central limit theorem formula, it is going to be our sample mean minus the population mean over the standard deviation divided by the square root of n. Okay, you've seen that many times before. So in this case, our sample mean was 1.05 seconds minus the 1.2 seconds over the 0.5 standard deviation divided by the square root of our sample size, which is 100 rats were injected. And if you do all this work on your paper, on your calculator, you will come up with a number of negative 3. All right, so this is your z-score. Z equals negative 3. Okay. All right, so now what we need to do is plot that on our graph. And I'm going to go ahead and take another color here for this. We're going to plot our test statistic in yellow. We don't have that here. So starting here at 0, where is negative 3? Well, it's to the left. We go right past negative 1.660 and 1.645. We're way, way out here to where this is our test statistic. This is where z equals negative 3. And I can write that as 0.00 if I need to. All right. Okay. So what does that mean? Well, step 5 is to go ahead and state our claim, right? So because our test statistic is clearly in the critical space, way out here, we definitely have enough evidence we are going to reject the null. Okay, we reject the null. And as you can see, whether you used a t score or a z-score for your critical value. It does not matter. In the end, your test statistic is far to the left of that, and so we know we can reject the null. All right, so when we reject the null, I like to just go right up here and let's just go ahead and draw a line right through that null. We are rejecting it. So therefore, we have enough evidence to accept the alternative, which happens to be the claim. So therefore, there is enough evidence to accept the claim that the drug will improve response time. Okay, we can go ahead and let the drug company response time, and go ahead and let the drug company make that claim. Okay, and if you needed to, in the homework, it might ask you why. Well, in this case, the reason is because it's in the critical space. It also is because -3 is less than -1.645 using the z and t values, or -1.660. But sometimes they want the p-value, and if we do it that way, the reason we know we can reject the null is because our p-value, which is if you go to the z-table, is virtually 0. You can look it up. In fact, it's 0.0017 is in fact less than our alpha, which is 0.05. Okay, so either way, we have enough evidence to reject that claim. So go ahead and give the homework, those last few problems in homework number 18. Go ahead and give them a try.